We will be conducting a two-way Anova in this video, and I've chosen the same setup as for the one-way Anova. We have 4 different synthesis methods, 1, 2, 3, 4, and we've registered the yield for each method, and we've used the method 5 times. Each of the methods have been run 5 times, and we registered the yield in each case. But it does so happen that each of these experiments were conducted in different labs. So I'll just note down here which lab took care of the experiments. And we have 2 lab 4s, so that's lab 5 here. Right. So lab 1 conducted experiments using each of the 4 methods, and so did lab 2 and lab 3 and lab 4. Now we might worry that each lab is not doing the exact same thing as the other might do. So that might introduce some variation in the yields here. It's a possibility that we cannot ignore. So how do we take that into account? And it really doesn't have to be labs. It could be different lab technicians, or it could just be the same lab technician, but different days, or some other variable that might influence the yield here. So what can we do to eliminate this extra variation that we might worry is introduced by this extra variable, which is the lab in this case? Well, that's the two-way Anova is the answer. So that's kind of the multi-sample analog to the paired t-test. This reminds you of the paired t-test where we had 2 samples where there was a connection between each of the observations in the samples. Well, that's the same case here, but now we have 4 samples, so we can't use a t-test. We have to use a two-way Anova. Yeah, let's just do it. So what we do is that we go into data here and choose data analysis, and we choose Anova 2-factor without repetition. And without repetition means that we only have 1 data point for each category. So this is synthesis method 1 in lab 1. So we only have 1 number for that. We don't have like 2, 3, 4, 5. So we have 1 number in each category here. So that's without repetition here. And we choose the input area by clicking here and marking the area here, and notice that I include the labels here, and therefore you should put a tick mark in this box here that we've included labels. The significance level is 5%, that's fine by me. And if you want the output inside the same sheet here, you choose this option. If you want a different sheet, you can choose this one. Right, let's click OK, and here we have the output. And of course this is in Danish, but I'll do my best to translate. This is some intermediate results that we are not really interested in to begin with. You can see the number of observations in each sample here, and in each block. This is what we call blocks. In the book they refer to these as blocks, and these are treatments. And the treatments are the ones that we're interested in. Right. So we computed the averages and the variance. But let's go down to the conclusions here. I'll zoom a little bit out here so we can see everything at once. Sorry. So here we have the rows, and in our case that means the methods. And in general we would call that the treatments. And here we have the columns, or the blocks. Or in our case, it's the laps here, and in general, we would refer to those as blocks. And this is the era, and I would like to refer to it as random or unexplained. Okay, so what we've done here is that we've computed the variation between the treatments, that is, between the methods here. And SK, that would be SS in English, so that's the sum squared deviation, the sum squared variation, if you like. And we calculated that between the rows, between the methods, between the laps, the 5 laps here, and then we also looked at the total variation, so to speak. So this represents, another way of thinking of this is if the laps are equal in the way they do this test or this experiment, there's no difference between the way the laps do this experiment, and there's no difference between the 4 methods. That's really the null hypothesis, right? That we have, and we might want to repeat that. Let's see if I can do that. Like that. The null hypothesis is that the 4 means are the same. The 4 yields, the 4 average yields of these methods are the same. So if that's the case, and there's no significant difference between the 5 laps, then we really expect to see the same number appear 20 times in this matrix here. And we would expect some kind of the average of these numbers to appear in all of these cells here. So why doesn't that happen? Well, part of the explanation that we have different numbers, not the same number in all cells, is that there is some difference between the rows, the methods, and there is some difference between the laps, and then there's some unexplained variation going on, something that we cannot explain using methods or laps, something that's might have some other cause, but we don't know what the cause is, so we'll just call it unexplained or random, or in this case error. And these sum squared deviations here represent those contributions to the total variation that we have here. This is the total. So the total variation in this data material we can explain using the difference in methods, difference in laps, and then there's part of it that we can't explain. And here we divide by the degrees of freedom in each case, and we get what we could call the mean squared deviation. And those are the numbers that we were really interested in, because this tells us how much variation there is between the methods on average compared to the total random unexplained variation in this experiment. If we hold these two numbers against each other, take this one, divide by this one, we get a ratio of variances, this number here, and that's an F statistic. It has an F distribution. So we can say something about whether this is an extreme number or not, and as you can see, it is an extreme number. The p-value is tiny, so it's way beyond the critical number. This is the number we would, if the F statistic was below this number, we wouldn't be able to reject the null hypothesis, but it's way beyond this critical number here. So we are definitely able to reject the null hypothesis. This variation between the methods is way beyond what we could reasonably explain using just the random. I mean, we can't blame this difference, this variation between the methods. We can't blame that on random variation. That would be, I mean, anything is possible in statistics, but it's very unlikely that this difference in the methods is due to random variation. Very unlikely. So this is kind of the number that we want to, this is the concluding number that is of interest to us. This is the number that tells us that we can reject the null hypothesis. There's another p-value here, and that corresponds to the lapse. The lapse have some variations too between them, and if we compare that average or mean variation to the random variation in the experiment, we get another F statistic. It's not as big, but it's still significant. It's beyond the critical, so we get a p-value that's less than 5%. What that means is that there is a significant difference between the yields that these labs get when they do the experiment. In other words, it turned out to be a good idea to keep track of what experiments have been conducted in lab 1, in lab 2, and lab 3, and lab 4, and lab 5. If we were certain that these labs conducted the experiments in very much the same ways, that there was hardly any difference among them, then we didn't have to keep track of which lab did what experiment. We could just erase those categories and we'll just look at it like, well, we did this method 5 times. We don't care about the lab because that doesn't matter. They do it perfectly the same in all labs. And we did experiment 2 5 times. It doesn't matter which lab did it because they do the same thing. But this statistic here and this p-value shows us that there is actually a significant difference between the labs. So it's a good idea to keep track of which lab did what experiment.